This is Lab 4 in Physics 2211 on oscillations. The objective of this lab is to observe the motion of a mass attached to an oscillating spring and compare it to a predicted motion of the mass using a computed model. Some physics principles we'll need to know are Newton's second law stating that the change in momentum is equal to the net force acting on the system times the change in time. With this, we can solve for the velocity update formula and the position update formula as shown below. The forces acting on the system are going to be the force of gravity and the spring force. The magnitude of the net force is going to be equal to the mass times the gravitational constant of the Earth plus the spring constant multiplied by the stretched or compressed distance of the spring. Here we can see the free body diagram of the forces acting on the system, which is the force of gravity and the force of spring. In this lab, we'll also need to know energy. In our lab, the system is going to be the mass, the spring, and the Earth. And because there are no outside forces acting upon the system, we know that the total work from the surroundings is going to be equal to 0. This means that the change in energy is also 0. However, in this case, our total change in energy is going to be equal to the change in kinetic energy plus the change in gravitational potential energy plus the change in spring potential energy, which is all going to be equal to 0. Kinetic energy is equal to 1/2 times the mass times the speed squared. Gravitational potential energy is equal to mass times the gravitational constant of the Earth times the height. Spring potential energy is going to be equal to 1/2 times the spring constant times the amount of distance that the spring is stretched or compressed squared. Here is a video I observed using Tracker. I chose my origin as the point where the spring was attached to the pivot position, and I then recorded the positions of the mass as it oscillated around. I then got the positions of the x and the y during the time intervals. Some known values of the system are that the mass attached to the spring is 0.402 kilograms, the initial position is negative 0.12 in the x direction, negative 0.63 in the y direction, and 0 in the z direction. The initial velocity is going to be 0 meters per second for all 3 dimensions. Another value we know is a known length of the spring at one point in its motion, which is 0.7 meters. With these values, I can now solve for the spring constant. However, in order to know the spring constant, I need to know the period of this oscillation. In order to do that, I found the amount of time it took for the spring to take 4 periods. So I found the time at this position and the time at this position, which was 4 periods total. And I subtracted the times and divided it by 4 because that's the amount of times that the spring oscillated. So subtracting these two numbers and dividing it by 4, I got 1.5195 seconds for my period of the system. I then solved for the K and got 6.874 newtons per meter. Now to solve for the relaxed spring length, I set the force of gravity equal to the spring force and readjusted the equation for the relaxed spring length, and I then got 0.127 meters. In GlowScript, I readjusted the values of the system's mass, the initial position, and the initial velocity shown as here. I then changed the gravitational constant, the spring constant, and the relaxed length of the spring. I then adjusted the equation for L, which is the length of the spring, and L hat, which is the direction of the spring, and S, which is the amount of distance that the spring is stretched or compressed. I then put in the equations for kinetic energy, gravitational potential energy, and spring potential energy. I then added the 3 together in order to get total energy. In this loop, I adjusted the total time. I also adjusted the force of gravity equation, the spring force equation, and the net force equation. I inserted the position update and the velocity update formulas. And I used the same equations for L, L hat, and S shown before. I then also solved for the kinetic energy, the change in kinetic energy, the gravitational potential energy, the change in gravitational potential energy, the spring potential energy, the change in spring potential energy, the total energy, and the change in total energy. So using this model, we can see here the system and the setup of our model and the total path, the path that our mass follows. We can also see the change in the energies shown in this graph, and notice how the change in total energy is always 0 throughout the oscillation. We can also see the x position versus time and the y position of the time of the model and our experiment. So what does this all mean? In this model, the energy principle is satisfied. With our system including the mass, spring, and Earth, there are no outside forces acting upon the system to do work and change its energy. As you can see from the energy graph, the orange line indicates the change in total energy. The change in total energy stays 0 throughout the model, and meaning that the energy in our system is conserved. If I decided to use the x values for the period of the system's oscillation, I would get 1.66 seconds rather than the 1.52 seconds from the y values. Using 1.66 seconds would create a smaller spring constant, leading to a smaller resting length if using the same measurements. This would lead to a greater spring force, creating a wider difference between the modeled and observed values. And the reason why we use the y values is because the direction of the spring is in the y direction and not the x direction.